In the final section of Chapter 13, we want to look at a few applications that involve the different processes of heat transfer. First, let's consider the thermal insulation that is used in the construction of homes and other buildings. In order to keep heating and air conditioning bills to a minimum, it pays to use a good thermal insulation in your home. The insulation is effective in two main ways. First, by placing the insulation between the inner and outer walls of the home, it prevents convection currents from forming between the two walls. Second, the thermal insulating properties of the insulation reduces the transfer of heat between the inside and outside of the home by limiting the conduction process. The logic behind thermal insulation comes directly from equation 13.1, which shows the relationship between the heat per unit time flowing through a material of thickness L. Keeping the value of Q over T to a minimum means using materials that have small thermal conductivities K and large thicknesses L. Construction engineers, however, prefer to use equation 13.1 in the following way, where they write the thermal conductivity in the denominator. The term L over K in the denominator is called the R value. An R value expresses in a single number the combined effects of thermal conductivity and thickness. Larger R values reduce the heat per unit time flowing through the material and therefore mean better insulation. It is also convenient to use R values to describe layered slabs formed by sandwiching together a number of materials with different thermal conductivities and different thicknesses. The R values for the individual layers can be added to give a single R value for the entire slab. It should be noted, however, that R values are expressed using units of feet, hours, Fahrenheit degrees, and BTUs for thickness, time, temperature, and heat respectively. Typical fiberglass insulation used in home construction has an R value that ranges from 2.5 to 3.7. Our second example of heat transfer deals with the protection of sensitive electronic equipment inside orbiting satellites. When it is in the Earth's shadow, an orbiting satellite is shielded from the intense electromagnetic waves emitted by the sun. But when it moves out of the Earth's shadow, the satellite experiences the full effect of these waves. As a result, the temperature within the satellite would decrease and increase sharply during an orbital period, and sensitive electronic circuitry would suffer unless precautions are taken. To minimize temperature fluctuations, satellites are often covered with a highly reflecting and hence poorly absorbing metal foil. By reflecting much of the sunlight, the foil minimizes temperature rises. Being a poor absorber, the foil is also a poor emitter, which reduces radiant energy losses. Reducing these losses keeps the temperature from falling excessively. As a final example of the applications of heat transfer, let's consider a common thermos bottle, which is sometimes referred to as a dewar. The purpose of the thermos is to keep hot things hot, like coffee and soup, or to keep cold things cold, like ice water or lemonade. A thermos usually consists of a double-walled glass vessel with silvered inner walls, and it minimizes heat transfer via convection, conduction, and radiation. The space between the walls is evacuated to reduce energy losses due to conduction and convection. The silvered surfaces reflect most of the radiant energy that would otherwise enter or leave the liquid in the thermos. Finally, little heat is lost through the glass or the rubber-like gaskets and stopper because these materials have relatively small thermal conductivities.